Well, hello again. We're looking at the exercises for Chapter 2, Section 4. These were little warm-ups or looking at examples of Dirichlet's theorem for particular cases. And so we've got two ones to look at here. Prove there are infinitely many primes congruent to -1 mod 3. That one's not very hard. It's done in the same spirit as we did in the other video. And question 11 is, we take a prime p and we're going to deduce that x to the fourth is -1 mod p is soluble if and only if p is 1 mod 8. And then we're going to use that to prove there are infinitely many primes of the form 8k plus 1. So infinitely many 1 mod 8 primes. And the hint here is to use this form, this number n, which is twice the product of these primes that we have supposed finite set of primes that are congruent to 1 mod 8 to the fourth plus 1. So here's the worked solution to these two problems here. So for question 10, we'd set it out in the same way as we did before. So we assume the contrary. We let S be Q1 up to QR be the set of all primes that are congruent to -1 mod 3. We assume there's only finitely many for the moment. And we put P, capital P, to be 3 times the product of these -1. So it's a slight variation on Euclid's proof. Now we just note that this P is -1 mod 3. So if it's prime, well, that's the end of the story, because P doesn't belong to this set S, and it's -1 mod 3 prime. So we have to therefore assume that this capital P must be composite, and if all of its prime factors are congruent to 1 mod 3, then the product of all of the prime factors is also congruent to 1 mod 3. And again, we have a contradiction, because we now have a prime factor that is if all the prime factors are 1 mod 3, their product is 1 mod 3, but we've seen up here that P is congruent to -1 mod 3. So that means P has at least one prime factor that is congruent to -1 mod 3, but of course that cannot belong to S, because each of these, when you divide P by each of these primes, you get a non-zero remainder. So the conclusion is there are infinitely many primes congruent to -1 mod 3, as there are infinitely many primes congruent to +1 mod 3, but that's harder to prove. The second, question 11, was we start off by looking at this equation x to the fourth congruent to -1 mod p. And I'm going to use theorem 1.1 again, which says this has solution if and only if -1 to the p minus 1 divided by the greatest common divisor of 4 and p minus 1 is 1 mod p. You'll need to look back to theorem 1.1 for that, but that's what it is. Now, and that's going to be true if and only if this exponent up here is even. So if and only if p minus 1 on the GCD of 4 and p minus 1 is even. Now, if p is 8, every prime has to be of the form 8k plus r, where r is plus or minus 1 plus or minus 3. And if you look at those four cases and see which one of these makes this even, then the condition only holds when r is 1. And so that means my p is congruent to 1 mod 8. So that tells me then that this equation has solution if and only if p is 1 mod 8. Now for part B, to prove there are infinitely many primes congruent to 1 mod 8, we again let S be, we assume the contrary, so let S be P1 up to PR be the set of all primes congruent to plus 1 mod 8. There are no others, according to the assumption. We put capital N to be twice the product of all of these to the fourth plus 1. Now, we now let P be a prime factor of n. Now P has to be odd, obviously, because this number is odd. And by part A, this thing here, if it's congruent to 0 mod P, implies that P is a 1 mod 8 prime. But again, this number n is not divisible by any of these p1 up to pr, so this number is not going to be, so this prime, which is 1 mod 8, doesn't belong to the set S. And once again we have a contradiction. Now of course all of these particular cases of Dirichlet's theorem, they have some things in common, but there's no way of getting a general result by using these special cases, which is why we need to, as we'll see in one of the later chapters, we need a more sophisticated way to prove the Dirichlet theorem.